Okay, okay, we see it. Yeah.
Okay. Very good.
Okay.
All
All right. Can you hear me?
Yeah, we can. We can hear you very well.
Okay, that's great. Okay.
Awesome.
So,
Yeah, I'll just introduce you and then you'll start.
okay, good.
Okay.
Okay. Thank you.
So it's my great pleasure to introduce Professor Qiang, and he was with sort of Hong Kong UST for many years, and he's currently the Chief AI Officer and the Director of Academy of AI for Hong Kong Polytechnic University. And so those people who have done this federated learning and the transfer learning, you probably know him very well. And he has been a pioneer for both those fields. And he also did a lot of applications in the banking domain for the federated learning as well as the transfer learning. And he has also been the chair of many conferences and the Qiang as well. And so he has done lots of interesting stuff, and his students are very successful as well. And they are successful in academia and also in corporate, sort of very high up in the corporate sort of world. And one of his students or two of his students are very successful entrepreneurs as well. And his son is a professional basketball player. Let's welcome Qiang to give us a talk.
Thank you, Bing. Thank you, everybody, for listening. I'm very happy to be here, especially talking at a lifelong learning conference, which is very dear to me because a lot of my work from very early on, I've been thinking about the question of how to make AI systems lifelong. So today my talk is Continual Federated Learning, and you can consider the title as Lifelong Federated Learning as well. So let me start by looking at some motivation. So first of all, let me introduce federated learning for those who are new to this field. So the idea is simply distributed machine learning with security, especially privacy preserving. So take one example in the banking domain. Suppose you are deciding, your system is deciding whether to approve a loan application, and you need to come up with a credit rating for a user. Usually, a bank does not have enough data. Although the bank may have a lot of samples for many users, for each user, the attributes or the features is very limited. The bank usually don't know what the user does outside this bank. But credit rating requires this kind of information. So to get to accurate information, a single bank has to work together with a bunch of banks and non-banks like internet companies and others in order to come up with a credible model. But such models can only be built in a distributed manner, and today must preserve privacy. User privacy requirement is very, very strong. And so as I list on the right-hand side of this page, besides credit rating, we ask how to jointly build models and how to do this while preserve privacy. And in case some banks want to opt out, and so how do we unlearn the data from these individuals in our models? And finally, how to do continual learning and lifelong learning. Okay, so there are lots of very, very exciting academic questions as well as industrial questions. The same thing actually occurs over and over again in other domains, such as medicine and in manufacturing, supply chain, and so on. Okay, so federated learning takes the centralized computing and look at its weakness and try to improve on that. On the left-hand side here, we see a little sheep and trying to grow up So the traditional way is to buy the grass from various uh, uh, repository and then come to feed the sheep. The sheep locates in the center. So this is very similar to centralized model building, where we take the data to where the model is, and in order to grow the model. But federated learning takes another way, which is shown on the right, where the sheep is taken to where the data is. That is the grass. And this way the sheep can grow, the model can grow. But if you are careful, no privacy is leaked out because we keep the grass where it is. So there's no trade secret leaked out. So in order to, so federated learning actually started out from Google, but then quickly caught fire in across the world. And it's a field that has grown very quickly. So such as indicated on the Gartner hype curve, where you can see it's on a very highly growing, rapidly growing trajectory. And thanks to many related fields, it helped the federated learning to grow extremely quickly. Fields such as multi-party computation, which is a branch of theoretical computer science, from encryption, from even hardware, and from database fields, which there are many excellent works on differential privacy and privacy preserving data access. So putting all these together with distributed and machine learning and model building, we have this federated learning as a new field. And so Google's original idea is to consider each client as an individual user holding some data. And so the question is how to build a global model which can benefit all, but without revealing the individual secret of a client. So to do this, they propose a Fed average, which is an average model version of the uh, uh, global model, which is contributed by each individual client through exchanging of parameters. Here, the parameters are encrypted in some way. And in this way, a model, a client A can learn from all the other clients, but without revealing the identity of these clients and without revealing the secret parts of the data from these other clients. So they can do this very efficiently. And we can also consider this as a peer-to-peer kind of federated learning, where we have two enterprises and they wish to build a stronger model by joining together their feature spaces. And this is done through a algorithm known as vertical federated learning. And so these are different paradigms. So I want to quickly mention that in the process, there are many open source software, and we contributed one of the first such software which became very popular. And this is a project on the Linux Foundation. Okay, so that was the very high level overview of federated learning. But when we move forward, we see several potential problems in federated learning. First of all, the security issue is not a single issue of just leaking some data labels out, leaking some identity out, but it is this security issue is with AI from day one. So on the left-hand side here, we see machine learning process in a very high level, where we have a training process and a inference process. And in each of these processes, if you look at how data are collected, how models are built, and how inferences are made, there are many potential areas where privacy can be leaked out. And therefore, when different parties work together, if you're not careful, it's very easy for us to leak privacy. Even when we only exchange parameters between different parties. And here on the right-hand side, a work from MIT showed that if two parties work in a um, uh, unprotected federated learning paradigm, then the privacy of data can be easily leaked out, even if they only exchange parameters. And so we have to identify different parties in a federated learning process where we have, of course, the model builder, which is the federated model part. But then we have protectors and we have adversaries. And sometimes these three roles are in one party or they are distributed among different parties. So there's nobody in this ecosystem that we can absolutely trust. But we have to collectively rely on everybody's effort to build a model. Okay, so the issue is very complex. So first of all, we ask whether it's possible to have a completely secure system and which can build a model which is completely efficient and the model is totally accurate. So this is very similar to the issue of return and risk kind of balance. Um, and so we prove that it is in fact impossible to achieve the maximum optimality on all three issues. And we call this no free lunch theorem. And so this basically placed a ceiling on what we can do. And this ceiling is can be considered as a optimization problem where we wish to generate the best model under constraints of privacy and efficiency. Um, and in fact, uh, mathematical uh, algorithms such as multi-objective optimization algorithms can help in this front. And if you look at this problem, we can find a space in which we can depict the best we can do under all three constraints, and this is known as the Pareto front. As shown on the right-hand side here, we see a curve, and this curve shows the best you can do under the three constraints, and you cannot cross this boundary when you try to optimize the system even further, which is getting even closer to the origin here if you want to minimize the risks and the losses. So the issue is how do we optimize this joint multi-objective optimization problem? And we did a lot of simulation experiments, and all of which point to this its necessity of balancing this and to in order to make this a working algorithm. So what we can do, in fact, is we can push this Pareto front even closer to the boundary if we can design the system more wisely. And so from this point on, I will show you several additional issues which make the problem even more complex. One additional issue is not only privacy is can be leaked out. There may be some parties which come in with malicious intention. And so maybe they even work together in a Byzantine attack manner, where they pretend to be ordinary users and contributors, but in fact, their intention is to cause damage to the collective model. And in such cases, researchers have designed various algorithms to detect such cliques or to prevent such attacks from happening. And so here we have not just three objectives, we have even more objectives, such as, finding out the malicious users and preventing them from more attacks. And we have the additional objective of incentivize people to contribute more of their data, contribute more of their effort, computing effort, and their models. And so such issue belongs to mechanism design in incentive optimization. So how do we incentivize all the parties and distribute the returns in a fair way in order to make the system sustainable? And if we design the system carefully enough, we can discourage the attackers from even thinking of attack, which is shown on the graph here on the left-hand side, where the green areas corresponds to safe areas. And our mechanism design can lift us into this safe area and prevent attacks from happening. And here I wish to add additional features to our work, which is if we design the incentives and design the algorithms properly, we can look at a potential platform and system for federated learning and give it a assessment. And such assessments are especially important at the governmental level because we wish the parties which work together using a algorithm and using some potential platforms to be given safety guarantees. And here on the right-hand side, we see a tree of potential safety guarantee, which is shown in colored labels at the bottom. The security can range from the basic level to the ideal level, depending on the threat model used, the type of data protected, the method to protect the data, and to build the models, to put all these together. So we actually work with local government agencies, and they created an agency to assess the IT industry's potential solutions and give them the periodic assessment, just like a health check. A system get this security health check. And there's even more work which I'm going to quickly go through and launch into topic of interest today, which is lifelong machine learning used in federated learning. And here I wish to reveal a little of my own work with my students and colleagues in lifelong machine learning. So as early as 2013, in a AAAI Spring Symposium, we proposed um, a paradigm for lifelong machine learning, considering the relationship between knowledge and inductive learning system and the data. But such a system was completely constructed in a centralized way. At that time, we focused on a issue of how to test whether a system is sustainable and can experience continual growth in a lifelong manner. And to this end, students of and my student and I proposed a new Turing test, which is taking a Turing test and adding a timeline to it. And so we wish the system to grow continuously in a monotonic manner in order to be considered intelligent. But later on, my own work ventured into transfer learning, which is today people talk about taking a pre-trained model and fine-tune it in various ways in order to solve new problems. And this is exactly the paradigm we worked on, which is taking a source domain and using transfer learning, which is fine-tuning to make it into to make the model work in a new domain, where the new domain can have new target, can have new model, or can have new tasks. So there are many variations of transfer learning. or lifelong machine learning in that manner. So this work, which strikes me with very deep impression, came from Stanford and World Bank, where they took a image processing model trained based on ImageNet data and used that to adapt to a satellite image recognition based on night um, images from satellite. And from the lights you can see from a satellite, you can roughly classify a region into different levels of economic activity, such that the brighter regions represent better or higher level of economic activity. And then you can do another level of transfer from that model into a daytime picture to recognize even more features and to do more accurate and finer detailed economic developed level assessment. And this is used by World Bank to assess the economic well-being of Africa regions. And when deep learning came about, deep learning and machine lifelong learning, transfer learning are integrated together so that models at different levels of deep learning can be assigned different degrees of transferability. So the closer to the bottom, to the input level, the features extracted there are more general and they preliminary, and so they can be more transferable as compared to the features you extract in a deep learning system that's closer to the task level. The task level are more specific. So this is demonstrated in this 2014 work, which is shown on the right-hand side. And so if we want to extend transfer learning from just one step to multiple steps, we are getting closer to a lifelong learning system or continual transfer learning. It can be called that way, where systems can not only learn from the past, they can also learn from the future. So when a new domain appears, and when we learn more about that, we can go back and review previous domains and improve, in fact, improve our models in the past. So we can do some kind of reflection based on what we learned today, say at a university, and go back to middle school and see if we can solve a problem, maybe using some new tools we learned, maybe integration and differentiation to solve a arithmetic problem in a more efficient way. And so the system can work forward or backward in a uh, uh, connected manner. And in fact, my student and I took this idea one step further. So we asked whether we can do transfer learning automatically. So if you have heard of the term auto ML, we ask the question, can we create something called auto TL? To do this, we have to have a lot of transfer learning experiences, and we use these experiences as pairs from a source domain to a target domain, and using what method, and we get what kind of result. So we put all these tuples together to form a training system to train a machine learning system. And that machine learning system will take a new problem and automatically find a source domain for that new problem and tell us what the best algorithm is for that machine learning algorithm to work under the transfer learning paradigm. So this is very similar to finding a point in a multi-dimensional space, and where we want to transfer from that point to another point in this space, and which manifold allow us to do this transfer in a better way. And so so we call this learning to transfer framework and came up with a algorithm which can work efficiently. Okay, so there are various ways where we can make this work. And so even very different images, they can implicitly learn from each other, we found out. Okay. All right. Then okay, so there are much more. So this whole conference is about lifelong learning. So here I want to focus on one thing in lifelong learning. That is, um, what about unlearning? Unlearning is like forgetting. When we live our lives or when we work at a, I mean, when we are students, um, we not only learn, we also try to unlearn. And we, at the same time, we try to prevent unlearning of something, right? So we want to do our review before our final exam because we want to prevent the unintentional unlearning of some key points which will be asked in final exams. But for something which we shouldn't remember, because remembering too many things will make us unfocused, then we will intentionally unlearn these things. So in continuous learning, we face two types of unlearning. One is the type of unlearning which we want to prevent. Another is the type of unlearning that we want to encourage. Okay, so how do we do this? So first of all, let's look at the issue of catastrophic unlearning or catastrophic forgetting in the process of lifelong learning. What if we forget some key concepts or models or even data in the process of lifelong learning and damage our learning effect? So on the left-hand side of this slide, I show some key issues that we face. So when we try to prevent catastrophic um, forgetting, we have to remember, right, here we try to do this in a federated learning framework. So as we move on in the timeline from left to right, we also have to look up down in a spatial sense to make sure that people can prevent people should preserve privacy and allow people to engage in lifelong learning. So this is federated learning is spatial lifelong learning. So people learn from each other and people learn from themselves. So when you look at yourself yesterday, you can take that as another person. So this way we can fuse together temporal dimension and spatial dimension. Okay, and we wish to have good performance in a spatial dimension and temporal dimension and ensure efficiency as well. Okay, so when we as I mentioned, we want to partition our work into two parts. One is to prevent catastrophic um, um, unlearning or forgetting. Another is to intentionally unlearn some parts. And why is that important? Now, when we look at this picture, uh, we have multiple people in a group, in a teamwork um, setting to learn a joint model. It is possible that at some time point, some client wants to leave this teamwork. Some people want to leave and ask us to remove their data or influence of their data from our model. And when that happens, we have a obligation by law to remove their data from consideration. So such things are required by GDPR and by many laws regarding data privacy. Okay, and in such a case, we have to intentionally remove such data. So unlearning the past intentionally becomes also is an important issue. Okay, so first of all, we can formulate the unlearning problem as a continual learning or lifelong learning manner on different time points. So here, time points can go from, in a discrete way, can go from time point 1 to t on a horizontal axis. And we here in when we formulate it as a optimization problem, we have to take care to look at the past loss as well as future loss and give them different weights. So let's look at some specific issues here. So I just mentioned that when we want to prevent forgetting, we have two issues. One is to look at the timeline, one the temporal dimension. Another is to look at the spatial dimension. In the temporal dimension, we try to prevent new knowledge from um, wiping out important previous knowledge, past knowledge. So this is the forgetting issue on the temporal dimension. In the spatial dimension, when people work together, we try to prevent the phenomenon where one client will dominate another. So we'll completely remove the influence of another client. So this is preventing catastrophic forgetting of certain clients' information and data and knowledge in a spatial dimension. So we have to take care to look at both dimensions. Okay, so the setting is this. So we have a timeline from left to right, as shown on the right here. And so at first we have a local model for task one, and then new tasks keep coming. So what we try to in federated learning manner, we when we work on task one, we have a group of 3 clients, and they will come up with a global model. And so we can see it's possible that the global model performs worse off than the local model. So this corresponds to spatial forgetting. And when we march on to task two, the performance of all three is even lower because some important information is wiped out. And um, so this corresponds to temporal forgetting. Okay, so we wish to overcome both of them. So there are several ways designed to address this. And with my colleagues, we came up with some preliminary solutions recently. And one of them is to treat each task individually as a binary classification task. And as we march on, we design different VAE classifiers and make sure they are separated and do not interfere with each other. And as we move on, we accumulate more and more such VAEs so that we can use clustering and other methods in order to combine their forces and build better models as we go on. And when we do that, we try to uh, take care of the spatial and temporal catastrophic forgetting problem. So but the problem with this is that as time goes on, we accumulate more and more VAE classifiers and the model will grow bigger and bigger in size, which is not efficient. And we have designed another method, which is looking at the forgetting problem at different levels of granularity. And so at some level and above, we wish the knowledge to stay constant. So we try to maintain the most preliminary knowledge and ensure that they are not forgotten. And we allow some still allow some forgetting to happen at the lower level. So at this point, we can compromise between the model size and the knowledge that are protected. So this is using hierarchical knowledge partitioning to ensure this compromise to happen. And another method was to uh, look at the two problems as a unified whole, so that we can take the problem and look at two things. One is the problem of forgetting may happen at parameter level. So when a new task comes, training happens for the new task. And so some parameters which are important for the previous tasks are removed, are erased. And so this happens within the model, uh, inside of the model itself, or it can happen at the task level. And so this is what we know, what we call output forgetting. So this will cause feature space shift. So to prevent these two from happening, we designed a number of important features and recognize them as important across the timeline, and recognize that they are um, one way that for them to be important is that they should stay constant. Okay, so and other features can change, but these important salient features should remain constant, and we call them anchor points. And so once we recognize these anchor points, we protect their positions in the feature space so that they stay constant. Okay, so in this way, um, as time goes, we recognize more and more important anchor points. Of course, at time point one, we do not have any idea. But as more time points are accumulated, we have better and better idea of what are the anchor points, and we can fix these features as we go along. And the anchor points can go along the timeline as well as across the spatial line. So all the clients are told what features are important, and they should not wipe them out as they learn new tasks. Okay, and the system works very well, especially the anchor point can be recognized using clustering of tasks, clustering of features as well. So before, above, I have discussed the issue of unintentional forgetting and how to prevent them from happening. And now, suppose some clients want to opt out and they want to take their data with them, and they ask the system to please take their data's influence in the model even. So how do we do this? Okay, so such systems are actually very important from a legal point of view, such as required by CCPA and by GDPR. When a user wants to remove their data from a group, such as request that their data not be used in a search engine or not be used in a large language model training, uh, the system people have the obligation to do this, to remove it. Although it's easy said than done, it's actually very difficult to take the data and its influence from a trained model. So how do we do this? I think this is going to be a long-standing issue in AI. And so here I show a picture of learning, unlearning, and relearning. So unlearning is taking some connections out. So it's not necessarily to take the result in a not so a less smart brain, but it makes the brain maybe less troubled by some data and becomes even more intelligent in the future. And the system can do this as well as in AI models today. When some users, as shown on the lower left, when some users opt out, the question is, can we then recognize some parameters that we must revise in order to satisfy the user's wish? And such a thing can be represented as a general optimization problem, which we show on the right. But to design algorithms is fairly difficult. And here I just show a very simple idea of learning, unlearning, and verification. And so the unlearning part is done by looking at, so first of all, which type of federated learning system we are facing. Is it horizontal, where we have clients learning from each other, or vertical, where clients are collaborating in order to strengthen their feature space? And here, when we work with federated learning, so if we have two clients, now if one client wants to leave, it's this if A wants to leave, B has to look at its model and take out the
Oh, this should be. No. Okay, share.
Okay, hello.
Yeah, we can hear. We can hear.
Okay, good, good. Yeah. So I'm sorry for the interruption. So but hopefully we'll get to complete soon. Um, yeah, so the question was how do we do unlearning? So the server receives a request and then can send can update a global model. That global model can then um, um, be downloaded to clients and update a auxiliary unlearning module. So the unlearning module purpose is to wipe out the influence of the living client. And so in this way, we don't have to reveal the privacy of the client that leaves the crowd, but we can make sure the influence is successfully removed. Okay, so as we work with federated learning system, another issue is because models are being exchanged between different clients. So there's the issue of how do we know which part of the model come from which client? And so we have to be able to protect the IP rights of the models, especially when we move along a timeline and at some point we want to ask which part of the model is contributed by which party. But a more uh, complex issue is um, we have to prevent the model stealing attacks and free rider attacks in our federated learning because we don't know which one will not contribute, and therefore they should not receive the benefits from the global model. Okay, so to do all these, we can consider a model as a artifact where we want to insert some secret code in order to be able to verify them when called upon. So we can trace the origin of the model, and we can work on this on a white box manner or on a black box manner. Okay, so if you don't know anything inside the model, we can still insert some potential watermarks in the model um, by adding additional training data and verify their computational results. I won't go into too much detail of the IP right objective. We have written a book on this and have discussed model IP right protection. But what I want to emphasize here is in lifelong federated learning, it's important to have this component as part of our system. Okay. So finally, I wish to say that I'm working with international team to on healthcare, especially aging related research, and in healthcare for the elderly. One, we have multiple clinics and multiple research labs working together, and they don't want to share data. Federated learning becomes important. And when we look at the longitudinal data of a person in the aging process, we are looking at a lifelong learning process. And so this is federated lifelong learning or federated continual learning. Okay, so let me summarize. So continual learning under a federated learning framework is both spatial learning and temporal learning. So here we particularly focused on catastrophic forgetting and also the opt-out privacy requirements. And there are various algorithms based on transfer learning and also federated learning integrated together. I think the potential is great, and our solutions are very preliminary, and I invite our colleagues to work together, and I look forward to more discussions with people. So here I should say thank you to my colleagues and my students who are shown here and from different departments. And here are some books, some in Chinese, some in Japanese, and others in English as usual. Thank you.
Any questions? Have a few minutes.
Regarding the unlearning problem and like the legal implications of it, one thing I'm struck by is that it seems like the law makes it like very black and white, like binary, whether or not the unlearning happened or not. Whereas when we define unlearning as a capability, there's many different respects of unlearning. I feel like, the obvious thing to do would be to like retrain from scratch without the initial data, if that's even possible. I'm just wondering, like, um, if you have any more detail on like, is this kind of thing viewed as acceptable to do these kind of is there kind of like more of a feeling like within reason you try to perform unlearning?
Right. Okay. So let's say you have you have built a language model based on a team of people's phones, and one of the person wants to go out, wants to leave, and also said that he or she does not want the data to be used in the model. And here you got a global model, and this person leaves. So at some regions in the world, such as in Europe, the requirement is when a person makes the request, the data must be taken out from the global model. And you are right. The obvious way to do is to train the model from scratch without that person's data. But usually such a thing would be extremely inefficient and would be infeasible. And so we look at it from a sustainability point of view. So we ask whether it's possible to take out the influence of that data and traces of the data to be removed without doing retraining. And sometimes it's impossible, but when it's possible, it's a great enhancement to efficiency and lifelong well-being of the model. Yeah, so it is in some cases it would be impossible, and in others there are cases where it is possible.
Okay, thank you. That clarifies.
Thank you.
Yeah, thank you for this presentation. So I have a question regarding the spatial and the temporal aspects of the continual federated learning. So the catastrophic forgetting is happening due to the spatial aspect or the temporal aspect. Can we segregate between them? Like, for example, in the non-ID case of federated learning, is the catastrophic forgetting which we are observing is due to the non-IDness within the client's data, or it's like how different distributions within the groups of clients is affecting the backward transfer or the forgetting? Can we segregate and handle it on a based on the distribution within the client's aspects?
Yeah, that's a great question. And I think you mentioned a very important point. That is, when we look at in a spatial way in federated learning, when the data distribution are non-ID, so in a way they are competing with each other when they form a when they work together. So it's very similar to when people are working in a team and they implicitly are also competing for influence. So here in federated learning, so each client is trying to influence the global model at the server. And in a non-ID sense, some are more dominating. So maybe they're because of their distribution, because of the weight of their distribution, or because of their popularity. Maybe there are three clients with the same distribution, and there's just a single client with another distribution. So all these issues of cases of non-ID can cause the catastrophic forgetting in a spatial dimension. Likewise, if we consider the spatial non-IDness happens on a timeline, at some point, maybe the data is so dominating along the timeline that it makes the system forget all the previous history. So that's another version of the catastrophic forgetting. So here, I think you touched on a very important but very difficult issue of non-IDness. There are ways to address this, such as using uh, so uh, 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 segregation, as you mentioned. We can look at each distribution group individually, and when we integrate between groups, we have to be careful not to let one wipe out another. So things like that.
I have another question. Yeah. So
Mhm.
in the federated setup, it's we cannot ensure like the data arriving at the clients are from which task. So if different clients are observing data from different tasks at the same time, how to do the continual federated learning in that setup? Any ideas?
Yeah. So so right in federated learning sense, data is very private, and so each client they want to protect their data privacy, and so therefore the global model should not know which part of the model come from which client. So in this case, if you want to do continuous learning, the server is also progressing along the timeline. And in this case, the server, I'm guessing your question is, how do you ensure the server learns in a consistent way, right? I guess,
Yes.
yeah. In fact, the server has more opportunities to learn, but it can be confusing. For example, when we look at a timeline as the days in a week, for example, say on Saturday, of course, you can learn from client ABC on Saturday, but you can also learn from so this on Saturday you can also learn from all previous days, right? So like ABC on Monday, on Tuesday, all the way to Friday. So there are implicit clients that are there that joins this federated learning ecosystem. So as time moves on, you can see more and more clients join into this learning paradigm. Although today's clients are more important as you progress in more and more into the past, their weight should be less and less. I think this will at the same time provide more opportunities for us to learn. At the same time provides more complexities for us to learn, because many of these data can be conflicting and can be contradicting with each other and non-ID in nature. Yeah, so this in fact is a very interesting way to look at the data as a matrix or tensor as we move along. I haven't thought about this, but thank you for the tip. Yeah,
Yeah.
so I think this is a nice way to look at the problem.
One more question.
Mm-hmm.
Can you compare how good the methods are for unlearning in the federated setting versus the non-federated setting?
All right. Yes. I think for unlearning in the federated setting is more difficult. It's more difficult, so it should perform worse compared to a centralized version, because not only you have to unlearn, you have to unlearn under privacy constraint, and so that's a huge constraint on what you can do. So let's say if you have a repertoire of 100 algorithms in a centralized setting, in a federated setting, maybe you can only use 30 of these to choose from. So I believe it's more difficult in a federated setting.
Okay, for the interest of time, and let's thank the speaker again. Thank you.
Thank you all. Thank you for
Thank you.
inviting. Thank you.